Good evening, everybody. Hope I'm audible to all of you. Can anybody confirm?
Yes, sir, you are audible.
Thank you. Good evening, all of you. Best GIS Day wishes to all of you guys. Um, yes, thanks for the introduction, sir. So, in this today's session, it's a 1 hour session. We'll be covering air pollution monitoring through satellite remote sensing. So, I'm planning to quickly run through the slides so that we can concentrate more on the practical session. So, yeah. These following few slides will be of basics of remote sensing, how the air pollution and pollutants can be uh, detected through satellite sensors. So, visible satellite images are essentially photographs taken from space. Sensors on board the satellites captures the sunlight reflected back from the Earth. So that is a basic ideology of remote sensing. Um, Earth observing satellite do not just take one picture, but they really observe the Earth in many individual wavelength bands. So each wavelength interacts differently with land, water, vegetation, and atmospheric particles, allows us to extract the valuable scientific information from it. RGB imagery. So, for example, if we assign the satellite bands to red, green, and blue display channels, so the result look like what we see uh, through our naked eyes. So, this is called the true color imagery. For instance, MODIS uses the visible bands of 1, 4, and 3 to produce the true color view of the Earth. So these are all the basic components of air quality monitoring using satellite remote sensing. So we can actually able to detect the pollutions and uh, profiling it vertically in the atmosphere, understand the transport of those dusts and smoke, compare the satellite between with using the ground sensors, turning the raw radiance into meaningful air quality metrics. So on the whole, remote sensing is not just imaging. There is a modeling involving behind it, science, physics especially, and interpretation. It's all the rolling circle behind the remote sensing. Why actually aerosol matters? Um, Atmospheric aerosol may be very tiny, but they are very impactful and massive. They actually reduce the visibility, affect the human health, influence the climate directly and indirectly, and helps to form the clouds as well. So it contributes to the acid rain depositions. Aerosol can originate from natural sources like dust storms or even through anthropogenic activities and human emissions. In 2013, air pollutant contributes to 5.5 billion deaths worldwide. Satellite helps quantifying this human impact more accurately than the ground monitoring alone, especially in the region where the dense sensor network. So, air quality is directly linked to the UN Sustainable Development Goals, where environmental, economic, and social balance is required. Achieving clean air improves the public health, productivity, and climate resilience. So, air quality monitoring works best with when we combine the ground measurements, airborne and satellite measurements, I mean observation, and atmospheric modeling. So, satellite basically fills the gaps where the uh, ground network are spare. So, what do satellite really measure? Satellite do not directly measure any of air pollutants parameters like PM 2.5 or nitrogen dioxide, etc. Instead, they measure the spectral reflectance, that is reflected or emitted energy. So then we can use the algorithm to convert the radiance into parameters like aerosol optical depth or nitrogen peroxide, sulfur dioxide, etc. So remote sensing process basically the transformation from radiance to meaningful pollution levels. That includes use the known atmospheric physics, apply the retrieval algorithm, um, compute the geophysical quantities such as air pollutants, and apply them in the air quality analysis. So, because different materials interact differently with radiance, we can design the imagery to highlight vegetation, smoke, dust, and water. So that's why water looks dark, cloud looks white, and pollution often looks very hazy. So we can observe the haze, clouds, fog, and low clouds also we can differentiate from the snow as well. So the true color imagery, uh, so this is actually true color imagery. Uh, the true color helps us to visualize the smoke and recognize the dust plumes and land cover features even without complex processing. Identifying features is easier when there is a clear pollution source in the scene. So this is false color composite basically. So in false color composite, we assign non-visible wavelength in the visible color. So this highlights the particular feature. For example, if we want to highlight the vegetation health or burn scars or ice and snow aerosol pattern. So we can actually identify and pick out the landform features that can be highlighted in the satellite imagery. So for that application, we are using the false color images. So this is the basic RGB difference between false color and true color. And we can easily observe the change in the vegetation color from the space itself. Here comes the AOD. So another few slides will be the major pollutants that can be retrieved from the satellite remote sensing. So AOD is the dimensionless value that represents how much aerosol blocks the light through the atmospheric column. Higher aerosol or higher AOD means more particle in the air. So ground PM 2.5 measures the surface concentration, whereas AOD measures the entire column, making the two related but not non-identical. So uh, basically, the PM 2.5 is retrieved from AOD. AOD means aerosol optical depth, and OT means optical thickness. So satellite measuring the aerosol, like for example, MODIS provides the daily global average, enabling us to track the smoke from fire, industrial pollution, dust storms, seasonal trend, etc. So, so here comes the aerosol trend over India. So, satellite data shows the strong seasonal change in aerosol loadings over India from the year 2004 to 2014. So this is the decadal trend, um, especially before and after the monsoon. So this map highlights the increasing urban and industrial influences on some area. For example, Calcutta, Chennai, all these metropolitan cities are filled with urban areas and industrial influences, which directly impact on the air pollution in the environment. Here comes the PM 2.5. So this maps from HOW um, and research models that shows the many developing regions still lack of ground PM 2.5 monitors, making the satellite based estimation vital for global environmental qualification. So this is basically the DIMOC model where the air quality modeling can be done by integrating many layers. So advanced system like the DMARC model combines the satellite AOD plus ground monitors plus pollution data. Also, that by all using all these data, we can simulate the model to generate the improvised PM 2.5 estimates with uncertain values. Now, MODIS, moderate resolution imaging spectrometer. So it is the workhouse for satellite sensors. So it imagery we can retrieve from 2000 to the present years, and it has multiple spatial resolution, day repeat coverage. So these are all the advantage of the MODIS, and it provides many products including surface reflectance, atmospheric products, and related properties, aerosol content, fire monitoring, vegetation indices, and etc. So these are all the comprehensive products that are available through MODIS Aqua and Terra. OMI, ozone monitoring instrument. So it measures the gases like NO2, SO2, O3. So it absorbing aerosol index. So it is widely used to detect the plumes cover cloud and snow, which visible imagery struggles with. Like so, these are all the influencing parameters, or the we can say the air pollutants that can be retrieved through OMI. Here comes MISR, multi-angle imaging spectroradiometer. So it has multiple viewing angles, which enables the aerosol height retrievals, particle and shape, um, particle shape and size emissions, which can be estimated, and it is especially useful for smoke and dust events. So this angle imaging spectrometer is lack in the MODIS. So this is the advantage over the MODIS by using MASR. Here comes VIRS. VIIRS, it's a visible infrared imaging radiometer. So it improves upon the MODIS actually. So it has wider swath, finer resolution, and new algorithms for AOD retrieval over bright land. Also, it's a current research over VIIRS. Also, it includes the smoke mass products for fire monitoring, forest fire monitoring. So all these are NASA products. Here comes the European Space Agency, that is from Sentinel satellite Tropomi sensor. So Tropomi actually it has the neighborhood scale resolution, and it can detect the NO2, ozone, SO2, methane, aerosol, formaldehyde, etc. So this enables monitoring of emission at the city level and even block levels as well, because it has a higher spatial resolution, 7 kilometer by 7 kilometer. We have other sensors like geostationary satellites uh, can observe the same region many times per hour. So it gives the excellent real-time images for fire, smoke, and dust tracking. So Geo 16 loop, this is for dust and this is for smoke. So this area is over southeast United States. This is Himawari 8 loop for fog and smog over Australia. So these are all the comparative analysis of all the sensors and products. So each sensor has its own advantage and strength. MODIS have high resolution and good coverage. MISR have better aerosol characterization. OMI and Tropomi has the uh, ability to track the trace gas, and VIIRS improves the resolution and continuity. So no single satellite does everything, but combined system can give the best picture. There are some limitations as well. So the challenges include only daytime optical measurement can is possible, and cloud blocks the view. Obviously, cloud coverage is a big disadvantage for satellite remote sensing, and accuracy varies across the surface types and altitudes, and limited information on aerosol chemistry. When it goes to the deeper level of chemical components, the information is very less from satellite remote sensing, and temporal resolution is only once per day. So early warning system or real time or near real time monitoring system for forest fire or dust storm are still it's in research and evolution. So these are all the data sources that where from where the satellite products that can be used for air quality and air pollution monitoring. So any questions from the audience I can tackle before getting into the practical session? Or let's just start the practical session and then we come for the questions part. Can anybody confirm that uh, you can see my Google
Sharat,
Earth interface? Yes, sir.
Mr. Sharat. So maybe if they have any questions, they will put that in the chat box, and maybe you can
Okay.
continue. And at the end, we can give around 10 minutes for the doubt clearance session. Okay. Yeah, I think that will be perfect. Is that all right?
Mhm. Thank you.
Yeah. Thank you. Thank you so much.
Okay. So, yes. So we are in the practical session. We'll be covering methane, carbon monoxide, formaldehyde, nitrogen dioxide, ozone, PM 2.5, and AOD. So one, two, three, four, five, six, seven. So seven pollutants we are going to visualize. And for this, all the seven air pollutants, I have taken uh, entire Kerala state. I can't say Kerala state, but the area covering the entire Kerala state I have taken because, of course, air is very dynamic and it can be easily flown between the surfaces. So choosing the steady area it is very important for air quality monitoring. So I have taken a bigger, large scale area. So with that covers the entire state. So yeah, so this is for AOD monitoring. I have just given the first up to sixth line. I have given the specified the coordinates of Kerala state, and then I have called the satellite name that is Copernicus from Copernicus Sentinel 5P offline level 3 data for AOD, and I have filtered the date from for this particular study July 2018 to present. I have taken. So I have filtered the date. So we are visualizing individual parameters, individual years also 2020, 2022, 2024. For all these 3 years, we are going to visualize the AOD. And for time series analysis from 2018 to present, we have taken. So I have filtered the date and I have filtered the cloud cover also. And I have just prepared the time series chart, giving the title, axis name, interval, etc. And I have add the legends as well. And for visualizing it in the map, I've given the separate 4 to 5 lines of code. So here comes the map. So let's just visualize for 2020. So this is for 2020 actually, and this is for 2022. This is for 2024. And here we can see the time series analysis from July 2018 to present. So we can see the abrupt change after the year 2021 to 22. So to visualize that change only, we have chosen those particular years, 2000. 1 minute. Yes, 2000, 2022, and 2024. Now let's move to CH4, that is methane. Similar kind of code. I've just given the steady area, that is the encovering coordinates that encloses the area of Kerala state. And so to note, for methane, carbon monoxide, formaldehyde, nitrogen dioxide, ozone, PM 2.5, I've used all these, sorry, AOD. All these are from Sentinel 5P level 3 data, but PM 2.5 is of MODIS. Only for PM 2.5, we are using MODIS data. Otherwise, we are using only the Sentinel 3 Tropomi sensor level 3 data. So CH4, for this, we are um, visualizing the CH4 concentration for the particular year 2020. Also, yearly average of CH4 concentration from 2019 to present as well. So this is the steady area, and this is the average CH4 concentration from 2019 to present. So yeah, we can observe most of the air pollutants are observed in the Ernakulam Kochi city area, where the industrial influences and affluences are very high. Also, the border of uh, Karnataka and Tamil Nadu as well have the high concentration of air pollutants, because since Coimbatore is very much near to the Kerala, Coimbatore is actually called as Manchester of South India. Like, it has many textile industry and other air pollutant releasing industries. So of course, the other sites, other anthropogenic activities also includes not just industry. Other activities also influence the air pollutants in atmosphere, but majorly industries are the high contributors for air pollution. So now let's just visualize the time series analysis. So this is the monthly CH4 levels from March 2019 to present. So we can see it's a gradual increasing trend of the increasing CH4 trend of the current state. This is for carbon monoxide. So the study period is 2017 to present for visualizing the map. So it is the monthly mean. It takes time actually to load. So red color shows the high concentration. So it most of the study area covers with the high concentration of carbon monoxide. Let's just visualize the time series analysis. So this is the monthly mean of CO concentration from 2017 to present. So all the Jan month of 2017, all the 2017 to 25, all the Feb month are stacked together, all the December month stacked together. So monthly average of the CO concentration is being exhibited in this graph. Now comes the formaldehyde, HCHO. So all these are the codes are very similar to each other. We are just giving the coordinates of Kerala state and we are just importing the Sentinel 5P offline level 3 data of each pollutants. And we are just giving the cloud cover and starting and ending date of the analysis. And we are just visualizing it. That's it. Let's just run this formaldehyde map. So here we have the 2019 to 24 month average of formaldehyde concentration over the study area. This is it. And for individual year, the concentration of formaldehyde is visualized for 2020. Let's just view the monthly average from 2019 to present. So the resources I have mentioned in the PPT, if you guys want it to to explore the resource site of all the layers, you can directly go to the website and download it, and you need a separate software to handle the data. Not just handle, to manipulate, to visualize, to map it, to analyze everything. You need at least a software. But Google Earth is a comprehensive cloud-based environment where the we don't need the storage space for anything to downloading and to save the data. The file can be easily retrieved from the websites, and we can visualize in the interface in the Google Earth engine directly. We can also adjust the visualizing parameters, like giving the different color palettes and giving the maximum minimum values by altering it in the code itself. And uh, we have the overall comprehensive holistic view of the layers. We can load how many layers we want, and we can also interpret through the layers, and we can establish the results through these uh, layer interpretation. So here comes the average of formaldehyde concentration from 2019 to present, and it is the 2020 formaldehyde concentration. So when it comes to air pollution, it's not just for land; it also covers the um, ocean area, because it's atmosphere, right? So it covers both land and water. So now let's just see the monthly average of formaldehyde levels from 2019 to 24. So it is also it's a stable up and down trend through all these years. Let's run nitrogen dioxide. So we have visualized 2020, 22, and 24. I think it's same of um, AOD, right? Yeah. We are just deleting the NO2 or CO2, CO, and giving AOD. Like it's all, the code is all the same. We are just need to give the different parameters name. That's it. Your coding is done. So now we have visualized the individual years of aerosol concentration. I think it's the same of AOD, right? AOD. I think the code of NO2 I didn't save, but NO2 is also like it is the same. Like if we give the NO2 concentration, it will like pop up. And here comes the ozone concentration. So it is also a monthly average of 2019 to 24. And this is for the particular year 2020. There is no much spatial variation that we can see in the map. Let's just look at on the graph where it is the monthly average from 19 to 24. So we can see the gradual up and down over the years also. So there is no much change we are observing this particular pollutant. Now comes sulfur dioxide. And this is monthly mean from 2018 to 25. So we can see the depletion of this SO2 concentration during the early 2021 and mid 2020, and it is a peak of this concentration in mid of 2023. So this gives the historical abbreviation and abbreviative and holistic approach over the years, so we can actually come up with what are all these influencing parameters, like whether it is of industry, whether it is of deforestation. So what is really the environmental impact that particular landform is going on. So we can actually go for EAA, environmental impact assessment over that particular area. And finally, here comes the PM 2.5 monitoring. So for this alone, we have used the MODIS data. So in MODIS, high resolution is being um, high resolution of the map can be retrieved. So obviously PM 2.5 is retrieved from AOD level, AOD data. So MODIS has its own sensor for detection of AOD. So from that AOD, we are retrieving by, by using the algorithm, and we are retrieving the PM 2.5 consideration from that particular AOD. Let's just run. So this is the AOD. Uh, since it is high resolution and it is a continuous data, it's taking much time to load. And also you can see the difference in this particular code. We have used the clipping tool to just clip the data, clip the map over the state boundary. Other is just appeared in the rectangle shape that covers the area of entire Kerala state, but in this code we have just clipped it over the administrative boundary of Kerala state. It's taking time. Meanwhile, we can visualize the temporal trend. So this is of 2024 particular year, uh, from January to December 2024, last year, where we can see the in the mm, uh, summer period it is on the peak, and it is slowly getting down when it starts with the fall, and it is also again it's peaking up on the mid monsoon period. Map have reached from Kasargod, it crossing Ernakulam, and it's going to be reached at Arapla, and we need to wait until it reaches Trivandrum. I don't know why it is taking so much of time. So AOD, since it is the dimensionless value, the area is full of gray, The map is full of grades, just single value showing the mean. But using the algorithm, we are retrieving it with spatial trend, and each uh, station points has its own value. And according to that value, the PM 2.5 concentration is differing from place to place. Is there any other code that I have left? No, we have covered all the 1, 2, 3, 4, 5, 6, and 7. So finally, this PM 2.5 is also covered. I don't know why it is taking this much of time. Meanwhile, if you guys have any doubts or clarification, uh, you can put it in the chat box, or you can unmute yourself and talk up. If you want to add any points or comments, suggestions on the presentation and on the practical session, you can. Anything is welcome. I think I have tons of scripts in my GE account, and also I have lots of assets. So that's why it's taking much time to load, I guess.
Hello, sir. Sir,
Yes,
am I audible?
yes, Yashwant, please.
Sir, actually, is Google Earth Engine is open for everyone?
Yes, it is open for everybody. You can create an account by using your simple mail ID, and you just have to give their purpose, whether it is
Okay,
academic research work or it's open source. It's not paid and all.
okay,
You easily open an account free of cost, and you can explore so much of satellite data, open source data, and you can uh, 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 do the analysis in whatever domain you want, not just in the air pollution or water pollution. You can use it for many other geospatial uh,
for
analysis.
forestry purpose, we can use it, right?
Of course, you can use it. Forest, it's in forest domain, forest cover mapping,
Okay,
forest fire, or greenery watch, or urban forest. In forestry, also it is very important, very much useful. But in forestry, the lack of data is the problem, I guess. High resolution data is the problem. With
okay,
high resolution data, if you want to go for high resolution data, you can opt for hyperspectral data.
okay,
It is better than the optical remote sensing and thermal remote sensing. It has both optical and thermal covered in hyperspectral remote sensing. It has 250 plus bands. You can individually analyze the up to the crop disease level, like tree by tree analysis we can do in forestry. Yes,
Okay. Okay. Thank you, sir.
thank you. So somebody in the chat box have s- asked some question. Could you explain the concept of NADER? So NADER in remote sensing, it is basically a point on the Earth surface directly beneath the satellite. So if the satellite is it's placed on a particular altitude in the atmosphere, that particular point which coincides with the center of the Earth surface, it is called the nadir point. So this nadir, I think in the presentation you have seen in the MIRS, I guess. So yeah, here MISR. So this is the nadir point, nadir image, that the straight angle. MISR has the angular observation capacity, so we can observe the land in different angles. That is basically the concept of nadir in remote sensing. Can we get rainfall data using this tool? Yes. Mhm. We can. The satellite sensors for rainfall is, we have IMD data that can be retrieved directly from the website, but using Google Earth Engine, IMD data can also be used, and that is called CHIRPS data. Not chips, but CHIRPS. CHIRPS. CHIRPS data for rainfall in GE. Oh, yes. So this is the data set where we can get it is freely available and it can be easily imported in Google Earth Engine. So please note this of chips data for Google Earth Engine. And also IMD data is also readily available, so we can also use that. Sir, could you please demo for any pollutants on particular area from starting? Yes, this is interesting. Let's just take AOD. Okay, so for AOD, we have three different uh, years: 2020, 2022, and 2024. So here we have taken the uh, area of Kerala. So I'll just take the area of any other state, say for example Gujarat, because Gujarat is also coast area and it is also having a number of industries near the coast. So let me just the Gujarat. Copy this. So with the help of AI, we are getting the coordinates of Gujarat state. Get. I just changed the coordinates. I didn't change anything even other than this change, other this coordinate change in this code. You can see the results. I think the coordinates are wrong. No, it's correct only. Yeah, it's covering. Yes, it's covering the entire Gujarat. You can see in the recent year 2024, high level of AOD in north part of Gujarat when compared to 2020 and 22. Sorry, 20 is a high, 24 is comparatively low, but 20 is very high. So yeah, this is like if you just give the parameter instead of this AOI into NO2, it will come and okay, Fahrenheit you can give or CO you can give, and you can also give the date difference like instead of 2020, 22, 24, 21, 23, 25 also you can give, but in 25 please make sure that you are giving the available data month, and that's it. Like it also shows the it came up with the time series analysis from 2018 to present as well. Any other questions? I can give you the code as well if you want. If you're interested, I can share you the code because these codes are retrieved from the direct Google Earth Engine catalog itself. So from that base, I have just done some debugging, done some enhancement in the coding, and I just for the webinar, and I have prepared all these scripts. If you guys want, I can share all the scripts to you. I will share the code. No worries. Any other questions, please? So for tomorrow's session, we'll be covering water pollutants. That is also the practical session is completely on Google Earth Engine. If you guys have Google Earth Engine account already, no worries. But if you don't have one, please create your own by today itself because it will be easier for you to practice on each day's practical session. It is very easy. You can just go to YouTube or something like how to create GE account. It will show step by step video. You can just it's just 2-step process. That's it. You can easily get it. I think if you guys have no doubts, then we can wind up the session. Jana, please unmute your mic. Thank you. Sir, how did you upload those particular pollutants? I'm a beginner for remote sensing, that's why I'm asking. I'm so happy that you asked the question at least. Okay, how did you upload the pollutants? Okay, so see, the traditional way of retrieving the remote sensing data from website of NASA, Copernicus. So NASA is it's it is a big organization. It has launched so many satellites and it has so many sensors, and those products of those sensors will be established for civil use. So from that website, we'll be going we'll be retrieving the data as files, which will be of some uh, some several GBs, and we need a storage at certain level. So we'll have to go to the website and we'll need to retrieve the data, and we need a software to manage it, handle it, and to analyze it to come up with particular result. We need a software. But Google Earth Engine, it's an effective platform which can be easily used to collect the data, analyze the data, and interpret and result. We can able to produce a result from that analysis as well. So it all in one platform. So how did I upload? Like I'm not uploading my data. I'm just calling out the data from that particular website. This is this just single line. Copernicus backslash S5P backslash OFFL means offline, slash L3 means level 3, AER means aerosol, AI means its level. So I'm just giving the data. So from the function get yearly data, bracket year, open bracket, return, EE dot image collection is the usual uh, code calling for the satellite data, and we are just calling out this particular satellite sensors data. So selecting the observing aerosol index, we are just filtering the date, what date we want, and we are just doing the mean processing of all those data, and we are just clipping over the Kerala state. That's it, and that's how we are calling out the satellite data for air pollutants from websites. Sorry, I wasn't sharing the screen. Who asked that question? Riju Krishnan. For you, I'm just again showing. To function get yearly data in the bracket year, open bracket, return to call the EE.image collection, Copernicus S5P offline level 3 aerosol data. Select the particular band, observing aerosol index, filtering out the date from which year to which year. So we are just giving the whichever year that is from available, and we are just giving the uh, uh, month and the date. So year from which it is available and to which it is available. And mean, we are just processing mean for each month, and we are just flipping it for Kerala. That's it. Yeah, I can share the code.
Hello, Sharath. Hello. Hello, Sharath. Sharath. Hello. Hello, am I audible to you? Hello, guys.
Yes,
Hello.
you are audible.
Yeah, thank you so much. And I think we promised you for the 1 hour sessions, and it is going to be 1 hour, or it is just past the 1 hour. And I hope that you people clear your doubts with Mr. Sharath Kumar. And if you have any further queries, then you can ask him tomorrow as well. And unfortunately, I had some network issues, so I didn't I was unable to give any comment on his sessions at that time in his presence. And we will meet tomorrow once again. And I hope that he covers almost all the questions that you asked to him. But if you have further queries, you just keep as a record, and you can ask him tomorrow. And at the end of the sessions, I would like to open it for a discussion. So everyone can interact each other. and also gain more knowledge from him. And if you need the PPTs, please let us know in advance, so I can request him to share at the end of the sessions. Okay, at the end of our program, and we are going to continue this one tomorrow on the same time, and you can use the same link to join. And if anyone is not registered properly, then re-register and re-register, and then you will get a personal link. Okay, personalized link for you. And okay, thank you, Felix, for your comments or the feedback on today's sessions. I hope you enjoy, and I really appreciate your participations. And I believe you are from Austria. And thank you so much, Felix, for joining our session. Thank you so much. So, anyone, any comments or feedback about the faculty that you can give in a form that we will provide you by the end of the sessions? Okay, thank you so much, and good night, or good night. Okay, thank you. Thank you.